Okay. Hello guys, in this video I would like to discuss about identifications of ions and also gases. However, before we move to the identification of ion, I would like to refresh your mind about the ionic charge. So this is what we call ionic charge. And we have what is called cations or positively charged ions. Since they are positive, means that they lack electron actually. So they lack electron. So they have thrown away their electron. Yeah, meaning that compared to their proton, they have lack number of electrons. While anions actually are, they have more electrons, so that's why they are negatively charged. So this one, they have more electrons. So these cations actually throw away electrons so that they become positive. So you can imagine that something, an atom, throws away a negative part of its life, so then it becomes positive. Makes sense, right? While the anions, originally they were atom, but then they receive the negativity, therefore they become more negative. So cations and anions are actually like give and take, because like cations throw it to the environment, and anions, they really want to take it, so they take it from the environment. So this is a bit on the ionic bond. If you would like to review on that, I have the video on ionic bond, so feel free to review on that. I would like to review just a brief here. So we have sodium, for example, which has 11 proton and 11 electron. 11 electron, they can be configured as such 281. And then 11 proton will remain actually in the nucleus. Since 281, and it's actually not full, so the shells are not completely filled. So sodium would actually find a strategy that when people look at sodium from the outside, people would look like, okay, sodium would be appearing full. So one of the strategy for sodium atom, it prefers to actually throw away this electron. So yeah, one electron away. So that when people see sodium from the outside, they will see this full shell. And then sodium will be very happy, I suppose. Now since sodium now has 11 proton and 10 electron, so now the overall charge will be +1, because proton actually gives a positive charge. So in this case, we have sodium +1 ion. So please remember this. While for example, if we have like Cl is 17, meaning that it has 17 proton and 17 electron, but the electron can be arranged as such 287. So it will try to find a strategy so that when people look at it from the outside, it will be full. It will try to get one more electron in, so that it will have 288, meaning that it will have 18 electron compared to only 17 proton. So in this case, the overall charge will be -1 or Cl -1. So it will only happen when the atoms are actually preparing themselves to do reaction, right? So imagine that sodium is the cation. The cation is sodium +1. So it's like a puzzle piece. And then the puzzle piece has one tip, because it's about to give electron, one electron. While Cl actually is about to receive one electron. So Cl -1. This is the anion. So then they will bind and they will create what is called by sodium chloride, NaCl, in this formula, NaCl. So NaCl or sodium chloride is a compound bond through ionic bond. It's not limited to just one puzzle piece. So let's say that here from the ionic chart, actually later I will also put this file in the description of this video. For example, calcium, we know that calcium is actually +2. So calcium is +2, meaning that it has the ability to bind, or like to have, it has two tips like this. And let's say that from the previous example, you know that Cl is -1 actually. So you know that the shape of Cl -1 is something like this. So we would actually need 2 Cls in order for the puzzle piece to be complete, so that the puzzle piece will be something like this. So this is the first Cl. So it will be Ca, Cl, and Cl. Shortly said, it will be CaCl2. or calcium chloride. So I hope that it refreshes your mind about the ionic bond and the form of compounds created through ionic. Okay, so the thing is that when we put this thing inside solvent, for example like water, then water actually has the ability to break these ionic bonds, meaning that originally from this one whole piece, then the water will have the ability, let's see, it will have the ability to break this. Yeah, so this one full piece will return back to their original puzzle pieces. So it will be separate, meaning that CaCl2 will actually form 3 puzzle pieces, Ca plus 2 and Cl minus 1 ion, and they will be swimming freely. The same thing happens to sodium chloride. For example, you put it inside water, so the water will be able to break the ionic bond as well, creating back these puzzle pieces. So sodium plus 1 ion and Cl minus 1 ion, and they will be freely swimming. So for example, this is the bigger glass, and then originally you put NaCl, this puzzle piece, the complete one. So now you have Na plus 1, now you have Cl minus 1, here also you have Na plus 1, Cl minus 1. So they are in the ion form, but they are freely swimming. Look, why is it like that? Why don't they just bind with the other? Well, because there is water. So the water is like, this is the water molecule, yeah? Imagine the water molecule is actually mixing thoroughly between the ions so that the ions cannot really bind to each other. So there are water interfering with them. And water is known to be a very good puzzle piece breaker. So that it's no longer in one big puzzle piece, but now it's in ions. And like they're buttering the ions so that they cannot touch each other to form sodium chloride back. So this is what happens to soluble things. So this is soluble. So let's say that sodium chloride, as you can see, the color of sodium chloride is actually colorless, right? If you compare sodium chloride to water, so let's say salt water, and drinking water, I would say that you would have a very difficult time differentiating them by color. However, of course, when we are offered an unknown drink, unknown sample, for example, then we would somehow have to test for any possible presence of anions or cations, right? Because we know that some ions are actually harmful for us. It can be toxic. For example, the presence of heavy metals, like the presence of lead ions. It can create cancer because these ions, this heavy metal ion cannot be removed from the body easily. So it will accumulate in our body. So it's carcinogenic actually. And there are other harmful effects on ions as well. It will disturb the balance in our blood. It will actually increase the job of our kidney, filtering the blood, and many others. And maybe for reaction, for reaction that are sensitive in ions. So we would need to be able to know the ions that are contained in a bigger glass full of water, for example, full of solution. And the way to do that, fortunately, we have some table. So for example here, this is the test for aqueous cations. So if you would like to test for ammonium cation, so the NH4 cation, the way to do that, actually the way to test for cations, we need to do two things in order to differentiate them. So first we add strong base, which is sodium hydroxide. So this is the first thing that we need to test for the cations. And second, we need aqueous ammonia. Well, ammonium would not react with ammonia because they are the same actually. So if you add sodium hydroxide to ammonium, actually the thing that will happen is that the solution will be base. So if you put litmus paper, especially red litmus paper, the litmus paper will turn into blue because ammonia solution containing ammonium, if you put sodium hydroxide, it will create a weak base solution, so it will turn into blue. Well, for example, if you have aluminum, so aluminum 3+, if you put sodium hydroxide inside, it will form white precipitate. So PPT means precipitate, yeah. Precipitate. Or like solid, yeah. Or like solids at the bottom of the bigger glass. So it will form solids like this. So the precipitate is white. And then if you add excess sodium hydroxide, it will be soluble. So the precipitation will actually be soluble. And the solution will be colorless. While if you add ammonia to aluminum, actually it will also form white precipitation. But if you add in excess, yeah, it will still has the solid. So this is actually how you differentiate the usage of sodium hydroxide and ammonia. Yeah? So initially, if you add like the same amount, like 2-3 drops, white precipitate will form. But if you add in excess, the one with sodium hydroxide will actually dissolve, while the one with ammonia will remain. So if a question is asking you that you have aluminum, for example, and then you're adding few drops, white precipitate will form. So at this moment, you haven't known whether it's sodium hydroxide or ammonia. But if the question gives you further information that if you add in excess it will be soluble, then we know for sure that it is sodium hydroxide. So this is how you read the table. So I hope that with this table it's clear enough and I don't need to explain that much. So note that, for example, zinc, white precipitate, and then it's soluble in excess as well. But for aqueous ammonia, white precipitate and soluble in excess as well. So meaning that this could be a good way for us to differentiate aluminum and zinc. Yeah, just react them with ammonia, aqueous ammonia, and react them with excess amount, because aluminum will still be insoluble while zinc will be soluble. Okay, so meaning that we can actually identify whether it's ammonium, aluminum, zinc, or whatever. So for example, calcium, white precipitate in sodium hydroxide. Calcium and ammonia, no or very slight precipitation, so very clear. If it is blue, then it's copper 2+ ion. If it is green, yeah, it's chromium but differentiated with iron, Fe+2. And if it is red-brown, it's iron +3. So this is how you test for it. Do you have to memorize? Yeah, yes, actually you kind of have to know and memorize this. So same like the test for anions, actually it's also kind of simple to read the table. So if you have the presence of carbonate -2, so this carbonate -2, CO3 -2, the test is actually to add dilute acid. So this is the way for us to test for carbonate. So if you suspect that your solution might contain carbonate, then please add dilute acid. Supposedly it will form carbon dioxide that makes lime water cloudy. If you suspect that your solution contains halogens or group 7, then you can add nitric acid and then silver nitrate. And then depending on the precipitation, you can identify them. So chloride will be white, bromide will be cream, and iodide will be yellow. And for nitrate ion, actually the way is to add sodium hydroxide and then add aluminum, and so on. So you can actually see the test for anions in this table. And then test for gas. The test for gas is actually not very chemical-like, as usually it's quite obvious. For example, like if you want to test for ammonia gas, then you can test from the smell and the color, and also a simple physical test. For example, here ammonia, you can just put a damp red litmus paper, and then the paper will turn into blue actually, because ammonia is kind of basic, right? It's not acid. For carbon dioxide, yeah, then you put lime water, yeah, it will turn lime water murky, creating white precipitation, for chlorine, hydrogen, and so on. So the test for gases can be differentiated by color and smell and also simple tests. However, for color and smell, yeah, indeed that most of the gases are actually colorless, so kind of difficult for us to see the appearance of the gas. Finally, the flame test for metal ions. So, if you suspect that your solution contains specific metal ions, aside from mixing things, like the previous one, like adding sodium hydroxide, adding ammonia, yeah, that can work. There are other ways for us to test for metal ions, which is actually flame test. So the idea is that we put unreactive wire, unreactive, meaning that this thing will not react with the sample. So for example, that the sample is KCl, yeah, potassium chloride. And we know that KCl actually comes from K plus 1 and Cl minus 1. So KCl is something like this. KCl. Inside water, inside solution, KCl will dissolve, forming K plus 1 puzzle piece and Cl minus 1 puzzle piece. So when you dip your metal wire, nichrome wire for example, nichrome is a mixture of nickel and chrome, but sometimes we use also platinum wire because they are unreactive. So the wire is put inside the sample, it should not react, it should not create something new. So then here in the small hole, some of the ions will still be there, right? So there will be potassium plus 1 ion and Cl minus 1 ion. And then you can burn it on Bunsen burner, and then specific color will appear. The reason why, because yeah, it will be discussed further in the upper grades, but technically the electrons will receive energy, and then some things will happen so that our eyes can actually observe. So every metal, they have different electron configurations, so that is why they will react differently on flame. So for potassium plus 1 ion, if you have potassium ion in your solution, then it will turn the flame into lilac, sodium yellow, lithium crimson, calcium red, and copper 2 plus blue green. So these are some refreshment for your mind about the ionic bonds, and also identifying common cations, anions, gases, and also doing flame tests on metal ions. I hope this video helps.